Hello, welcome everyone. Hopefully you can hear me okay. Welcome to this A-level session today, and do feel free to say hello in the chat and ask any questions as we go through, and also answer them as we work through some exam questions. But welcome, I hope everyone's keeping well. We've got a big kind of topic today as part of the calculus. We're looking at something to do with differentiation, which is very much a part of the pure maths side of the A-level course. So we're going to be looking at the quotient rule today. But welcome if you've joined, or if you're just joining, do feel free to say hi. It'd be lovely to see comments and questions coming in the chat. So I hope everyone's keeping well and having a good weekend. This is, as I said, quite an important differentiation subtopic today that's part of the pure maths side of the A-level. So it'll be really good to work through that with you. Do feel free to say hi. Lovely. Hi, everyone. Welcome. I can see the chat, so it's nice to see your messages coming through. As I said, we're about to get started. We've got quite a big topic to pack in and look at, and it would be great to get questions and answers as we go. Hi, guys. Welcome. That's great. So I'm going to just share the screen and we'll get started straight away. But do feel free to say hello if you haven't already, and we'll get started. So we're going to be looking at the quotient rule today. Hopefully this is now sharing the slides and we'll work through these questions together. So we're going to look at quotient rule. Welcome. Hi, everyone. And yeah, hopefully that's nice and full screen and you can see that. So let's begin. Quotient rule. So just quickly, I'm Max. I'm head of maths at Snap Revise. I did a maths degree before I started teaching, and I've been teaching A-level over quite an important transitional period, I think, where the course changed, and it's really nice to see kind of the old course and the new, and obviously the changes in the last couple of years. So it's been a really good time to sort of be teaching the A-level for me. I've really enjoyed seeing the changes and also getting to grips with what we need to all be aware of now on the course. So that's a bit about me, just about Snap Revise briefly, and then I'll talk a little bit more about Snap Revise at the end. Welcome again to all those joining. We're looking at quotient rule today. There is this offer that I'm going to talk about at the end. Back to School 21 is the code, and I'll talk about what to do with that towards the end of this session on the courses we offer on the Snap Revise platform, that, as I said, are geared up very much to the brand new exams, so the new A-levels and the new GCSEs, all of that sort of stuff. Snap Revise has been working on the resources and the courses being tailored specifically to those new changes and everything. So there's loads of stuff on there, and I'll talk about that towards the end. So the discount code is there, but as I said, towards the end, I'll show you where you can use that and what kind of stuff you'll have access to. So to start with, let's crack on with quotient rule. As I said, it'd be great. Welcome to everyone joining. It's amazing to hear so many people joining from all around, and lovely to see the comments in there. So that's brilliant. We're going to look at quotient rule, as I said, and specifically look at the derivatives of simple quotient functions, how to use the quotient rule, and then build into some slightly trickier examples as well. So that's what we're going to be doing in this session. I won't be doing like differentiation from first principles or graph sketching. It's very much this skill. This is a big skill in itself and is absolutely tested. So this is A2. This is very much like a year 13 extension of the topic. So differentiation, hopefully we're all aware of, is something in pure maths that we look at in year 12 and 13, but this is the kind of harder side of it. This is more towards the A2 content. So just as a recap of some of the stuff that we should know, hopefully from year 12 and also a little bit from year 13, this is almost sort of prerequisite knowledge if we're going to do the quotient rule. So differentiating polynomials, remember you sort of times by the power and then drop the power by 1. And then also, for example, here, if you've got multiple bits, you just sort of differentiate them all separately and do the summation of all those different parts. Welcome. Right, so then this next one, we have got differentiating exponentials. So this one here, does anyone know what this bit would differentiate to? So this is a little bit different, obviously, to a polynomial, differentiating e to the power of ax plus b. So what happens here, this is kind of like using the chain rule, absolutely. So what would happen is you differentiate the power and times it by what we've got. So this is sort of towards, I would say towards the end of the pure side of the maths course. but obviously integration follows this, and there's a few other little topics. So I would say that this would probably appear in the first term of year 13, depending on how your school or college or wherever you're doing your A-levels are structured. But it's quite a big fundamental idea in the pure content. Right, so let's have a little look. Differentiation rules that we learn in year 13. So this one here is a chain rule. So a function or a polynomial to a power, you kind of differentiate around it. So times by the power, drop the power by 1, then times by the derivative of the inside. So who recognizes that as a rule? So that's kind of like a version of the chain rule. And then what we've got is a more sort of specific chain rule. So chain rule is for composite functions, which means functions inside functions. So what you do is you basically differentiate the outside function of whatever's going on, and then multiply it by the derivative of what's happening in the kind of inside function. So this is sort of one way of denoting it. But do let me know if you're familiar with chain rule, as it seems like some of you are. Then this is different. This is a product rule. So this last one, this is when you've got two functions times together. And the way you basically do that is differentiate one and times it by the other, plus the other way round, differentiate the other and times it by the first one. So that's a product rule. So these are both versions of the chain rule, and this one here is what we'd call the product rule. The other thing we should hopefully be aware of, that would be handy to know, is differentiating how we differentiate sine and cos. And you do learn this from first principles, but it is also good to be able to recall this. So sine actually differentiates to cosine, and cosine differentiates to minus sine. And then this is sort of like a chain rule scenario of it. So this would differentiate to a cos ax plus b. And this one here would differentiate to minus a sine of ax plus b. Okay. Familiar to people. Do let me know though as we go if you have any questions or you want to check anything. That would be brilliant, and do feel free to answer questions as we go forward through this as well. Cool. So this topic, as I said, is very much a key part of all A-level courses. So whatever exam board you're working with, whether it's AQA, OCR or EdXL, the quotient rule and the different rules for differentiation are very much a key part of all of the A-levels. So we're going to look at the quotient rule now, and look at a way to deal with quotients. So effectively like functions that appear like fractions where there's a division going on. So the way we would deal with this, if we were to start with this one here, now how we could treat this function is we could think of it as trying to find the derivative of x squared to the power of minus 1. Does that make sense? So we could treat it like a chain rule. We could say, okay, it's like something to the minus 1. Does that make sense to everyone? So there are ways of sort of sidestepping and avoiding the quotient rule, but it does help if you know the rule when it becomes more complicated. So do we all see that we could treat that as x squared to the minus 1 and then go, okay, so it's a chain, it's a function in a function. So if I differentiate around it, minus 1 x squared to the minus 2, then times it by the derivative of the inside, which I end up with minus 2x over x squared squared, and I get minus 2x over x to the 4, which does actually simplify to minus 2 over x cubed. And there's various ways you could have done that kind of year 12 style as well. But I wanted to just show you that you could treat this like a chain because that will be handy for some of these more involved. Hopefully in a similar way, everyone's happy that we could as e to the 3x all to the power of minus 1, and then do the chain rule on that. So times by the power, drop the power by 1 and multiply by the derivative of the inside. Does everyone sort of follow what we're saying there? So this is using the chain rule to be able to do this, which is one of the rules you do before you go on to quotient rule. So hopefully it's happy that we can rewrite it in that way. And then what we would get is we'd get minus 1 e to the 3x to the minus 2 times by the derivative of e to the 3x, which is 3e to the 3x. And so what this would become is this would become minus 3e to the x over e to the 3x squared, which we could tidy up as minus 3e to the x over e to the 6x. Okay, so that's that one. Now we're going to look at some slightly harder examples here and then actually derive a quotient rule in general. So this is sort of muddling through using chain rule and using what we already know, but we're going to come up with a more secure rule that we can kind of quote for this style of function. So here we go. This one here. So this time we can treat it as what I'm basically trying to differentiate is x squared multiplied by e to the 3x to the minus 1. So this is now a chain and a product, and it's getting kind of quite complicated. So you have to do the derivative of one times the other way round. Oh, sorry, plus the other way round. So what you'd get is you'd get 2x e to the 3x to the minus 1 plus the other way round, which would be x squared times the derivative of that, which we just found. And that came out as minus 3e to the 3x over e to the 6x. And so that becomes a little bit nasty to write, because what we end up with, and if I leave that as e to the 3x all squared, I can write it as a single fraction. So what you could do is you could go, okay, so this is the same as 2x over e to the 3x plus x squared times minus 3e to the 3x over e to the 3x squared. So if I want to make a common denominator, I can kind of times this one here by another e to the 3x. Is I get this thing whereby, I'm just checking the chat, I'll try and answer these questions as we go. Yeah, so we're kind of covering a lot of topics. I'll talk about the regular web classes that we are through the whole course, and I'll show you that towards the end, and hopefully that will make more sense, because I do appreciate, obviously, everyone's school structures probably the way they work through the content quite differently. So you might not be doing this topic right now, or you may have covered it already and be doing something completely different. So yeah, this is very much quite an involved pure maths differentiation subtopic, and requires, you know, some more knowledge of differentiation as well. But yeah, as I'm showing you, this does start to get quite complicated doing it this way, and would be really handy if we have a rule. So if I just do this one quickly, show you what happens, we might be able to kind of work out what's going on and come up with an underlying rule, because we might notice some key things. So what we have is this one would be like e to the 3x times x squared to the minus 1. So again, it's a chain and a product. So you could differentiate one, times it by the other, plus the other way round, which would be keep that as it is, and times by the derivative of the other one, which would be minus 2x over x squared squared. And then what we would get is this would become 3x squared e to the 3x minus 2x e to the 3x over x squared squared. And you might think, like, why is he not expanding x squared squared? You can, but I want to show you how this ties into the rule. So what happens is when you try and make a common denominator, when you have a scenario that's got effectively a chain and a product in it. There's always going to be two bits that you're then going to want to write as a single fraction, which is why the quotient rule that I'm about to derive makes this a lot easier. So if we look at kind of creating a rule for this, what we've basically done for all of these problems so far is we've dealt with a scenario where we have like f of x times g of x to the minus 1. And that's what's been quite nasty to do, because the derivative of f of x is what it is. And the derivative of this bit is actually what's making this a little bit nasty. So the derivative of g of x to the minus 1 is a chain. So that comes out as minus g dash x over gx squared. And that's where the thing starts getting a little bit complicated. So to kind of combine this as a single rule, and we're kind of doing a product as well, what we end up with is we end up with f dash of x over g of x plus minus, because this one's a minus, we end up minusing off f of x, g dash of x over gx squared. So what we're going to do now is derive the quotient rule that comes about from this. This is very much like a general scenario. So then what this would become as a single fraction is the derivative of basically the top bit, the other, minus the other way round, all over the bottom function squared. So it does look nasty, but it will always end up being this rule. So when you've got a scenario where you've got f of x over g of x, some function of x over some other function of x, the quotient rule boils down to the derivative of top times the bottom minus the other way round over whatever was on the bottom squared. And you might still think, wow, okay, that's going to take a minute to sort of process and be happy with that. But what we'll do is we'll look at it with some very good examples and scenarios and make sure we're practicing just plugging into that rule to save us going through a chain and a product every single time. So that is the quotient rule. Who is familiar with the quotient rule? Who has actually seen it before? Has anyone done it before? So for some people, this might be revision. For others, this might be brand new. Okay, lovely. Thank you for questions and commenting and stuff in the chat as well. That's brilliant. So some of you may have seen this. For others, this might be quite a new idea. Let's keep going then. So just give me a quick indication of how you're feeling, and do absolutely be honest with if you're feeling okay. And if you haven't obviously done chain rule or product, this will be quite tricky and challenging, but hopefully still a bit insightful into where the differentiation goes and how involved it gets. No worries. Okay, so what we'll do, I'll do it with some examples, and it will hopefully bring to light some of the ideas a little bit more. Because understandably, if this is a very new idea, even the notation is really tricky. So I absolutely appreciate that. Of pure maths topic today. So what we'll do it with some examples and hopefully show you that the rule is actually okay to use once you know how to differentiate the separate parts. So I'll just rewrite the rule out, what the quotient rule actually is. So when you've got a scenario of f of x over g of x, a function over a function like this thing over this thing, two totally different functions, the way we differentiate that is we basically go, okay, it's the derivative of whatever's on the top times by the bottom minus the other way round, the derivative of what's on the bottom times by the function on the top over the thing that was on the bottom squared. So the first bit of working we'd do is we'd work out the different derivatives. So I know f of x is sine 2x. I want to know what its derivative is. Does anyone know what sine 2x differentiates to? Then the other one, which hopefully is a bit nicer, g of x is x squared, and we should all hopefully be able to differentiate x squared. It is a little bit, but some of that stuff has been watered down or removed from some of the A levels, so it's not. It's a very specific process. Very good. So this one here is 2 cos 2x, and the derivative of x squared. Hopefully, we're happy is 2x. Well done, guys. That's brilliant. So now we've kind of got all the little bits we need. We just need to plug it into that rule. So what we're going to get, if I plug into that rule, is I'm going to get dy dx. Well, let's piece it together. The derivative f dash of x, which is 2 cos 2x, 2 cos 2x, times by the g of x, which was this one, x squared, minus the other way round. So g dash of x, which was 2x, times by f of x, which was sine 2x, all over g of x squared. So that would be x squared squared. And that is actually technically done now. You have done the differentiation. That is it. We could potentially tidy it up a bit, because what we actually have is there's a common factor of x, because there's an x squared and an x here that could come out. And you could go, this is 2x cos 2x minus 2 sine 2x. And I factored an x out. And then on the bottom, it's over x to the 4. So that could cancel with one of those and leave x to the 3. So you've done the differentiation by this stage. You've plugged all the stuff in. This last bit is just me sort of tidying it up and giving it as a single fraction like we have done is really handy. So minus 2 sine 2x. So just check you're happy with how I tidied that up algebraically by factoring out an x and sort of cancelling it. So actually, once you've found all the separate derivatives and functions, you are just plugging into this rule and then just tidying it up where possible. So we'll do it with more examples now, and perhaps even some slightly nicer ones to really kind of get this rule across and show that once you know that rule, you are just plugging simpler derivatives in. Okay, so here we go. Here's another one. Do feel free to ask, stop me, or make me go back if you want to double check anything. Right, this one says use calculus to find the coordinates of the turning points of C. Right, let's not worry for a minute that it's asking us turning points. Calculus and turning points means we need to differentiate it. So what we're going to do is I'm going to think, right, let's remember dy by dx is equal to whatever was on the top differentiated times the bottom function minus the other way round, and then all over the bottom thing squared. So let's think, what's f of x? What's f dash of x? And hopefully these are nicer derivatives to do. These are more like year 12 style differentiation questions here. So the function on the top was x, so that should be okay to differentiate. The function on the bottom was 9 plus x squared, so that should be okay to differentiate. So what is the derivative of x? So f dash of x, what would that be equal to? This one here, what would we get? So this one would be equal to, differentiate x, we get 1, and differentiate 9 plus x squared, lovely, is 2x. Thanks, guys. So now, like I said, we've got everything we need to start subbing in to the quotient rule up here, and then we've effectively done the differentiation. So let's do that. So we're going to get 9 plus x squared times 1, which is just 9 plus x squared, minus the, oops, that was a bit strange, minus the other way round, which is 2x times by x. Okay, all over 9 plus x squared squared. This is dy dx. So hopefully we can see how I've plugged into that rule. I'm going to just tidy this up a bit. So 9 plus x squared minus 2x squared would be 9 minus x squared, because that bit is the same as 2x squared. And this is all over 9 plus x squared squared. Okay, now, if that's it, that's differentiated, we've done it. So like I said, once you know the rule, when you're plugging stuff in, it can actually boil down to something that's quite doable. The rule just looks really nasty when you're first deriving it or coming up with it. So what we do now is we're asked to find the coordinates of the turning points of C. So what do we do in like a year 12 scenario? If I'm asked for turning points, what do I do with the derivative? And this is a really good one for exam technique, because you could be asked this in year 12 or 13, and we still need to know the method that it's getting at. So if we're asked for the turning points, the coordinates of turning points are where the graph is at a maximum, minimum, or point of inflection. So basically when the derivative is equal to 0. So we're setting whatever we get equal to 0 and solving. And it's actually not that bad, because a fraction can only be equal to 0 when the numerator part is 0. So all we're really solving here is 9 minus x squared equals to 0. And it does say turning points, plural. So let's solve this. So this would mean x squared is 9. So x is equal to plus or minus 3. Is everyone happy with that? Well done. Yeah, so we've set it equal to 0. Superb. And that's going to be how we determine the turning points. So we set it equal to 0. So really, when that happens is when the numerator is equal to 0. That happens when x is equal to plus or minus 3. So what we know is we know the x coordinates of the turning points are plus or minus 3. So what we can do with that is then we can say, right, it did actually ask me for the coordinates. So I need the y values as well. So I just put 3 and minus 3 back into here. And so what we would get is plus or minus 3 over 9 plus or minus 3 squared. So that would come out as 3 over 18, or 3 minus 3 over 18. And so what we'd get is 1/6 or minus a sixth if we plugged 3 back in. So the coordinates of the turning point are 3, 1/6, and 3, minus 3, minus 1/6. So what we've done is we've used the quotient rule. The separate derivatives and parts weren't too bad to work out. Then we plug them back into the rule, tidy it all up. And then we think, right, why was I actually using calculus? What did I want to work out here? I wanted to work out turning points. So I'm setting it equal to 0. So that means really when the top bit is 0. Solve the value of x that makes that work, or the values of x, 3 and minus 3. But just bear in mind, it said coordinates, so you would be expected to give the y values as well. So that was a good question. And actually for the marks, considering that this is like a year 13 question, it's recapped some year 12 content. And actually the understanding of it is okay. It's just you've got to be really careful and make sure you know the quotient rule to be able to do this. But the actual level of the differentiation wasn't too involved. Cool. So what I'm going to do is I'm going to move this on and look at applying the quotient rule further. Please do ask any questions and keep submitting answers as you have been. And we'll look at a few more examples here and how to sort of simplify as well for different exam scenarios. So here we go. Simplifying quotients. Now, what could make this a lot easier is actually if we simplified the fraction first. So this in itself is a different skill. And the way you're going to go about simplifying fractions is actually factorizing. Just like with numbers, you sort of cancel them down. So before we actually differentiate, let's just check if we can factorize this and get some sort of simpler fractions. Now, what I would suggest is if you notice like the bottom is a difference of 2 squares. Say, for example, you found that one easier to factorize, because I personally would prefer factorizing that because I can see it's a difference of 2 squares. What's really good is that can often help you to factorize the top, because it kind of hints what the factors could be if you struggle factorizing something like this. And so this one actually factorizes to 2x minus 3 x plus 1. Now, what's brilliant about this is that this fraction was just a complicated way of writing x plus 1 over 2x plus 3. So this could be part A of the question. It could be a scaffolded question where part A says, do you know what, simplify the fraction. That's one skill ticked off. Now differentiate it and now do something else. So hopefully we can see how that has simplified to that. Now, what that means is now the derivatives of each of the different parts are a lot simpler. So I can now think about, right, that's f of x over g of x is what we've got going on here. So let's think, what's f of x, what's f dash of x, what's g of x, what's g dash of x? And if you guys could let me know, that'd be brilliant. Hopefully this is year 12 style differentiation now for each of these bits. So the function on top we know is x plus 1. Function underneath, the one on the denominator, is 2x plus 3. So what is the derivative of f dash of x? What is that derivative there? And what is the derivative here for g dash of x? So f dash of x, if we're differentiating x plus 1, that would differentiate to 1. And if we're differentiating 2x plus 3, what would that become? 2x plus 3 would differentiate to 2. Okay, so now what we can do, excellent, is sub this in to the derivatives into the quotient rule. So what we're going to get is dy by dx is f dash of x, which is 1, times by g of x, so 1 lot of 2x plus 3, minus the other way round, so 2 times x plus 1, all over the function that was on the bottom, 2x plus 3 squared. And so what we end up with is 2x plus 3 minus 2x plus 1, 2x plus 2, so we end up with 1 over 2x plus 3 squared. And that's it, all differentiated. And it was made a lot easier by simplifying the fraction first, which the question may or may not guide you to do. But again, by this stage, it was quite simple differentiation. It was just remembering the quotient rule and plugging it all in carefully to get the job done there. So good, let's look at another good example that we can try and simplify first of all. Now this one here suddenly looks a bit more involved because it's got trig in it. Can anyone tell me how the top bit could factorize? Any highest common factor we could take out that might help us with this? So this is very much tying in with the year 13 trigonometry as well. But the first bit we should be able to factorize hopefully something out regardless of if we've done that topic before. So let's think about if we can write this in a slightly simpler way. So do let me know. And really well done to everyone today. Well done for persevering through quite a full-on topic. This is very much an A-level, top-end A-level pure maths topic that is quite involved. So really, really well done. And thank you for working through this. We're going through, we're not shying away from tricky examples here. So it's great to see the comments and great to see that you are persevering through this, because it is kind of all leading towards this sort of stuff in year 13. And you need to be able to kind of tackle this head on. So that's brilliant. Right, so something that factorizes out here is there is a common factor of cos x. So I'm just going to start factorizing the top. And that would be times by another cos squared x to make cos cubed x minus sine squared x. Minus sine squared x. I'm going to show you some little tricks for this as well. All over sine 2x. Now, there is something you do in year 13 as well called the double angle formula. And sine 2x, you learn a little identity that can actually be written as 2 cos x sine x. So all of these little tricks help us sort of cancel things out. So I can rewrite sine 2x as 2 cos x sine x. So this is why a lot of you will do the trig chapter first, because it will allow you to do this topic a little bit more easily. There's another identity as well, that cos squared x minus sine squared x is cos 2x. So we end up with cos 2x over 2 sine x is what this boils down to. Please let me know if you have seen that topic before. I'd be interested to see who's done that double angle or addition formula in trigonometry before. because you might then be able to see how it would boil down to this. But as you can imagine, this could be, again, part A of the question that gets you to tidy it up in that form before you start differentiating it. So this is now a bit easier to differentiate if we've got it like this. Lovely, that's great to hear. So some of you have seen that bit of trig, and it might be that actually that's the point in the course you're at. You've done the trigonometry, which a lot of schools like to do as they start back in that first half term, and then work towards the calculus. So that's brilliant if you recognize that part of it. And as we can see, that does tidy up problems like this and allow us to go, okay, I can actually deal with this even better now because I know how to deal with the trig. So that's fantastic to hear that a lot of you have seen that before, or that some of you recognize that from the trigonometry chapters, and we can start to see its application in other things. Okay, fair enough. So the trig is massive as well. Like the trig is quite a big part of this course, and you can hopefully see why it's really important you do it in that order, that you understand the trigonometry before you start trying to do the calculus of year 13. So that's really good to hear from people there. Lovely. So now I can still do the same process. And the nice thing about maths in general is that once you do know a process, it is just a bit of practice and you can kind of replicate the idea. So again, a bit of trig going on. We're going to differentiate each bit. So 2 sine x would differentiate to 2 cos x. And then it is again just plugging it into that rule. So let's have a little look. So just a little reminder of what the quotient rule was, and then we'll whiz on. So remember that the quotient rule was the derivative of the thing that was on the top times the other, minus the other way round. And as I said, guys, really well done. Even if this is tricky, hopefully it's nice and insightful for when you come to it, you kind of know what to anticipate from the topic. That could be helpful in itself. So I'm using like a stylus to write this on here. And yeah, which I think, you know, is kind of can be quite tricky for maths, can't it? And so I appreciate as well those answering in the chat can be quite tricky. So very well done. So tidying this up, we get minus 4 sine 2x sine x. And as you can imagine, questions can ask you to write it in a certain form or a specific way. But this is all to do with fluency and confidence with these ideas, particularly the trig. So that's why spotting identities and understanding how things tidy up is really kind of quite handy. And you could be asked to sort of tidy up further. So that's brilliant. Right. So the quotient rule is very specific. It's for when there is effectively a fraction of 2 functions. That is when you'd use a quotient rule. A product is when there's 2 functions times together. And a chain is when it's like a function in another function. So a lot of the time it should be, with enough practice, fairly clear which one it's lending itself to, because it will be a specific sort of style. So they won't say that, they never say in the exams really the words chain, quotient, or product. They'll say differentiate this function or find the turning point. They very rarely say using chain rule. I don't think really they ever say that. Because, yeah, these rules are kind of mechanisms for the process of differentiation. So, yeah, it should be, with enough practice, it should be obvious which one is lending itself to for differentiation. Yeah, brilliant question. Good. So, guys, give me a little indication. I know some of you were feeling a little bit like it was a bit tricky earlier, but that's understandable and that's absolutely fine. Please just give me an indication of how you're feeling with that stuff. And obviously, if this bit's here you haven't covered before, that's no problem. At least hopefully this has been quite insightful. We've tackled quite a big topic to this point today, and we are going to be doing some exam style questions just after this to kind of consolidate what we've done. And then, as I said, I'll talk about Snap Revise and some of the upcoming web classes, but also the courses that we have on the platform that should hopefully be able to help you as well. So give me an indication in the chat, just a 1, 2, or a 3, or an emoji. That's lovely to sort of show how you're feeling with this content. And then what we'll do is we'll do a couple of exam questions, show you sort of the marks that are available, and give you an idea of how that's broken down and what would be expected in the exam. That's lovely. It's lovely to see that some of you are feeling a bit more confident this time round. It is tricky. It is. And if you haven't done some of it before, I'd be absolutely the same. I'd feel like, well, this is brand new And let's all be honest, it's not easy. It's maths A level, and it's the top end of it. So well done for all of this, guys, so far. And once we start using the rule, hopefully that's given everyone a bit of confidence. So let's look at these exam questions. I'm going to push this on now, but thank you for giving me a little indication there. So here we go. We've got an example here where part A is actually 7 marks for not doing any differentiation. This is actually a completely separate skill. This is something that is probably worth working through, but it's very much just algebra. We're not actually asked to differentiate it until here. And then it's just a 3-mark quotient rule. So the first part is the really involved bit. The first part is like manipulating the fractions. So see if you're kind of happy to do that and how confident you're feeling with that bit, because this is the first part of perhaps year 13 or what you'd be doing later in year 12 as well. So what we do is we want to combine it into a single fraction, but the first bit we'd probably do is, again, look at the factors and look at how we can make this one single fraction. So 2x plus 3 over x plus 2 minus this other one that could perhaps be factorized. And then let's get that and cancel it down if we can. So let's see what we've got. We've got 2x plus 3 over x plus 2 minus 9 plus 2x, and I'll help you guys out and factorize this one for you. 2x minus 1, x plus 2. And again, use the question to help you factorize it. So you might have noticed x plus 2 is probably a common factor. So to write this as a single fraction, who has done this chapter so far in year 13, for those that are in there, and you might have even done it in year 12. Combining a single fraction, we need a common denominator, which would be 2x minus 1, x plus 2. And what we would have to do is times this fraction here by 2x minus 1 over 2x minus 1. So we would get 2x plus 3 times 2x minus 1. Does that make sense to everyone? Because we need a common factor. So we're like timesing it by 1 in a clever way. And then this one we don't need to change. So this bit just stays as it is. And then, as I said, this isn't even differentiation, this part. This is just tidying up a fraction. So what we'd end up with, it's a little bit tedious, but for 7 marks, I think that's sort of fairly generous. 4x squared plus 4x minus 3. 4x squared plus, let me just check that. 6x minus 2x, 4x minus 3 minus 9, and also minus 2x, because really that should be in brackets, shouldn't it? Lovely. And then what we're going to do from there is that's all over. Let's keep it factorized. 2x minus 1, x plus 2. And the good thing is we know where we're going with it. So if you did struggle to do this in the exam, just thinking about exam technique, what's really good is you could still do part B and come back to it, because they're telling you what it should end up as. So the good thing with the show that is it doesn't stop you doing the rest of the question. So 4x minus 6 over x plus 2 is what that would sort of refactorize back up as, because that becomes 4x squared plus 2x minus 12, which refactorizes as this. And I appreciate I'm going through this bit quite quickly, but I'm kind of obviously keen to get onto the quotient rule here. And that becomes 4x minus 6 over 2x minus 1, which is what we wanted. So that's 7 marks if you thought, oh, I couldn't have done it that quickly, or it was quite involved. Don't worry, because you can still do part B and come back to it. So the good thing is you can kind of get as far as you can and then still carry on with the question. And that's what we're going to do. We're now going to look at part B, which is actually the quotient rule. And it's not a bad quotient to do, because remember, this is the sort of top function. Whoops. And I'm going to rewrite the quotient rule for you guys to remember, and do feel free to work ahead of me and get it. So it's the derivative of the top times the bottom minus the other way round all over whatever was on the bottom squared. So it just looks way worse than it is. I suppose like the first time you learn the quadratic formula, it feels like a real genius idea, but actually with all the kind of, because the notation looks a bit confusing, but then actually it's quite something you use all the time. So the derivative of the top is 4, the derivative of the bottom is 2. So it's really not that bad to plug into this formula. So what we get is the derivative of the whole thing confusingly, they've used f of x as the actual function. So the derivative of the whole thing is derivative of the top 4 times by what was on the bottom, minus the other way round 2 times what was on the top, 4x minus 6. Do check I'm not making any intentional mistakes. That's good, all over 2x minus 1 squared, and then tidy up if possible. So we expand it all out, 8x minus 4. Welcome, guys, if you're just joining, and thank you again to everyone for working so well through what is a really full-on A-level topic. It's been lovely to see, hopefully, kind of bit of a boost in confidence over something that initially was quite tough, and still does require a fair bit of practice, but there we go, there's the derivative. So really, in terms of the work that we had to do for the differentiation was nowhere near as much as part A, which was actually more of an algebraic tidying up fractions type skill. And that's what we get. So we get that as the derivative there of that quite complicated looking initial scenario. So most of the groundwork for this question was actually the algebra and tidying up fractions. Cool. So let's have a little look. I'm going to keep pushing on because I'm kind of mindful of the time here. So here we go. This one here, show that the derivative of that comes out there, and then it kind of the question carries on. So let's have a little look at the following. So if we're going to differentiate this one, let's again look at what's on the top and what it would differentiate to, and what's on the bottom and what that would differentiate to. Okay, so what we've got is we've got 3x squared plus 6x, and do feel free to work ahead of me. Then, as I said, guys, I will talk quickly about snap revise and some of the bits we've got going on, and also the discount code I'm going to sort of share with you again. But yeah, let's get this one done. This is a really good kind of exam question to round this all off. So g of x, remember, was x plus 1 all squared. So if I was to differentiate that, it would be, yeah, good sense of achievement if we get through this. Oops, sorry guys, my pen's gone a bit funny. Well done if you got that. Be 2, whoops, 2x plus 1 to the 1. There we go. And then what I can do is plug this into the quotient rule and hopefully end up with this. So again, it's good because it's a show that. So what we get is we're going to get dy dx is equal to f dash of x, 6x plus 6, which some of you worked out, that's superb, times by the derivative of the top, x plus 1 squared, minus the other way round. And I'm going to show you some little tricks for this one as well, which would be 2 lots of x plus 1 times by 3x squared plus 6x minus 7. Now, my hint would be don't expand this all out. I'm going to show you a little shortcut. Now, the way to shortcut it here, it's x plus 1 squared squared. So that would be to the 4. Now, the shortcut, I don't know if any of you guys have worked this out, what might help here, is x plus 1 is a common factor. So we can actually factor out x plus 1 on the top, and we'd have 6x plus 6, put a big bracket, and another x plus 1, minus 2 lots of this bracket. And then that will help us, because if we can factor out something like that, we can cancel it with one of the x plus 1s on the bottom. And this does often happen with this style of question. So what would happen here is this 4 could cancel with that and become 3. And then if we carry on expanding it and tidying it up, we do end up with 20 on the top. So I'm just mindful of the time, but you guys could perhaps work through expanding that up and tidying it yourselves, and you'll get to that stage. And then for the last part of the question, for part C, hopefully you recognize that the second derivative just wants you to differentiate that again one more time. And then what we'll do is hopefully come out with minus 15 over 4. We're going to solve that equation there. So I'll quickly whiz through this one. Welcome if you're just joining. I'm going to now differentiate 20 over x plus 1 cubed, again, using the quotient rule. So the derivative of the top is 0, and the derivative of the bottom part would be 3x plus 1 to the 4. So what this will actually differentiate to, so that was dy dx, and this is the last sort of exam style question we'll look at, and I'll talk about snap revise and give you guys the discount code again. This would become -3 times 20, and you could also do it like this by a chain rule, and it will come out as -60 over x plus 1 to the 4, which you could set equal to -15 over 4 and solve. And if you guys want to finish this off in your own time, because as I said, actually no, we've got time now to go through this. Just basically, like a year 12 style question, you're going to solve it equal to this value. So find when the second derivative equals that. This is actually just, again, very much algebraic. All the calculus is done. Yeah, so I'll quickly recap in a second what we've covered today. No problems at all. I'm just going to finish this question off. X plus 1 to the 4. X plus 1 to the 4. Then if I full fruit it, x plus 1 equals plus or minus 2. So x equals 1 or -3. And obviously feel free to screenshot or come back to check this. So basically what we've done today, and then appreciate that these were a bit quick, these final examples, but it gives you an idea of the sort of size of the exam questions and how this topic could come up. But actually, as you can see, it comes up in very much an algebraic way a lot of the time. And a lot of the marks aren't even for the differentiation. So hopefully that's kind of nice and clear. Well done to everyone for picking up quite an involved rule. So what we've looked at today is the quotient rule. Now, for anyone that's joined late, the quotient rule is basically when you're differentiating a function over another function. And so the way to do it, the derivative that we've just learned, ends up being the quotient rule. I'll write here. This is the rule you want to learn. It's effectively the derivative of what was on the top times by what's on the bottom, minus the other way round, derivative of the bottom times by what was on the top, all over the bottom bit squared. And then actually we found that when we were subbing into that, it wasn't too bad to carry out. It just looks quite daunting to start with. And this is very much one of the harder parts of the pure maths of year 13. So it's really, really involved part of the differentiation. I think you guys have picked this up brilliantly. As I said, I'm looking at the questions and comments in the chat. I'll just talk briefly about Snap Revise and let you know about some of the upcoming web classes and the resources we have, because some of you were asking about how we cover the course and how the topics are chosen and stuff. So basically the Snap Revise courses, I'm just going to navigate to the site now, comprise of web classes every week. So we do a year 12 and a year 13 web class, followed by drop-ins. So if you have, oh yeah, absolutely, you can use the letters V and U for the differentiation. I've just seen the question there. But as I was saying, we have a web class for year 12 and 13 every week, followed by a drop-in. So if you've got random questions from homework or upcoming exams you want help with, the drop-ins are often really useful. But on top of that, we have really nice tailor-made content for all the brand new A-levels, and it's bang up to date and in line with all the specification points that the exam boards have set out. So the revision notes are really kind of beautiful and clear, easy to follow. There's diagnostic quizzes, smart quizzes that kind of tailor the package to what you've learned and where the gaps are in your knowledge. And as I said, every kind of point is finely tuned with the actual syllabus of the exam. So it's really kind of a clear and easy to follow structure. So regardless of how your school or college is structuring the A-level, all of the mechanics and the stats is covered and can be found and navigated through really easily and kind of self-led. So the platform is set up incredibly well, I certainly think, but really easy to follow and easy to allow you to access the course in your own way and at your own pace. So it is really worth checking out the Snap Revise courses. And what I'll do is I will take you over to that. So here is the code, if you're interested, for 25% off. I'm going to stop sharing that quickly there and take you over to the site. So just to show you how to access this, hopefully that's sharing with you now. If you go on courses on the Snap Revise site, let's just try that. Courses, go start free trial. And what we've got, for example, for the maths course, there's loads. So you've got year 12, 13 mock papers, each topic broken down with videos, and it will jump you through the videos of really clear notes based on the diagnostic quizzes. There's exam packs that you can kind of make tailor-made, and the solutions are all there in line with the mark scheme. So you can make it easy, medium or hard. And it kind of allows you to work through the course at a really nice pace. I think everything's super clear on here. Everything's really easy to follow and easy to jump through as well. So you can kind of take ownership of what you've learned and push through at a really nice sort of pace. All the topics broken down, all the specification points really clear. And aside from that, as I said, we have the web classes. So you have the upcoming web classes, the times, you can download the presentations, and you also have a catalogue of all the other web classes that have been done and drop-ins as well. So that's for all year 13 and all year 12 topics, for pure maths, for stats and for mechanics. And the way we've structured the course is really very much in line with what most schools would probably follow. But as I said, the drop-ins will allow you to kind of deviate and ask anything that you might want to find out as well for topics you're currently doing in school. So that would be definitely something worth checking out if you've enjoyed these sessions. Obviously, we've got the YouTube sessions once a month for each subject, but every week there'll be a different subject on. So keep an eye on that and set reminders for the Sunday sessions. I hope this was useful and really well done. It's lovely to hear the feedback and also see some of the answers and questions coming in live as well today. It would be lovely to see some of you on Snap Revise, following and taking part in web classes in the future. But as I said, there's some brilliant resources on there that will hopefully help you with the A-level over what I'm sure has been quite a challenging couple of years for having to kind of take ownership of your learning. So really well done to all of you. And thanks again for working so well today. It's been lovely working through this content with you, even though it was pretty difficult stuff. So really well done to all of you. Keep well, enjoy the rest of your weekend and have a great week. And yeah, thanks again to everyone for taking part. Hopefully see you at a session soon. Well done, guys. Take care. Bye.